Statistics. We will learn some of them which are commonly used with examples and the merits and demerits of measures of dispersion, followed by a little knowledge check. We have covered in our previous sessions the left branch of this diagram, that is the measures of central tendency, the locations, mean, median, mode, geometric mean, harmonic mean and weighted mean. Now the other two branches of this diagram, they talk about the spread in the data. Statistical word for the same is dispersion. To learn the concept of dispersion, we also need to learn about what is meant by quartiles and percentiles, which help us to proceed further in understanding the measures of dispersion. So, dispersion denotes how stretched or squeezed a distribution in the data. It could be a theoretical distribution or whatever you have collected the data upon. It summarizes the internal variation or variations between observations. Now, the key question is, why should we learn dispersion? Aren't the measures of central tendency enough to give us the idea about the entire data? Because if you remember, whenever we started the central tendency, we were trying to say that we wanted a representative number which will indicate the entire data. So, if the measures of central tendency are doing that job, then what is the need of learning dispersion? For that purpose, this is a favorite picture of mine. From the context, it is clear that this person is trying to swim in the river and he has gone by the board, average depth 3 feet. Assuming that since the average is 3 feet, he can just take a nice dip into the waters. But the average depth 3 feet doesn't mean everywhere the depth of the river is 3 feet. No. So, if he doesn't have the idea about the variation as far as the depth of the river is concerned, then this is the situation he is going to end into. Okay. So, that happens with the data and the knowledge about the measures of central tendency only. So, if you have known only the measure of central tendency like mean or median or mode, but no idea about the variation in the data, then there is a tremendous problem. Because there could be several data sets for which the mean could be the same, but the spread in the data, that means the extent of the range, the values are going to be, or the response variable is going to be, that could differ. So, one has to understand about the extent of range or spread in the data values. Now, having digested this concept, obviously the first thing that comes to our mind is the range in the data. That means what is the maximum value, find it out. What is the minimum value, find it out and take the difference between the two. This is called as the range of the data. So, this is the crudest measure of dispersion. For example, here are 5 observations. The minimum is 3, maximum is 9 and you take the difference and you say that the range is 6. You know that we always come across range of temperatures. In news, we see the ranges of the temperatures because they depict the minimum and maximum temperature for a number of cities. So, that gives us the idea about the variation in the temperature across different locations. So, this is one simplest measure one can think of about dispersion. Simple example once again. Find the range of the following set of data. Here they are arranged into ascending order like we arrange them in while computing the median, but it is not necessary for computation of range. You just have to pick the minimum value and maximum value and compute the difference. That's it. Now with range, there are obviously some problems. First of all, it is the crudest measure of dispersion. If you have several observations which are of the lesser order of magnitude, I mean all observations are very lesser magnitude values and only one extreme observation, that's the maximum value, then the range is going to be unnecessarily very high. So that's the crudest measure of dispersion. So then statisticians thought about other measures of dispersion. Another drawback of range is that it doesn't take into consideration all other observations. It just thinks of the minimum value and the maximum value. So now we will learn the other two important measures of dispersion. One is the interquartile range and the other is variance or standard deviation. In order to know the measure interquartile range, one should know first of all what are the quartiles. See, you know median now. What does a median do? The median is the middle value, that is it below which there are 50% of the observations and above which there are 50% of the observations. So essentially the median is a positional average which splits the entire data into two equal halves. So why can't we think of some such other splitting values, some such other partition values? We can. So the lower quartile Q1, one can consider that it is the median of the first half of whatever you have got from the splitting by the median. So Q1 is the positional quantity below which there are 25% observations. Likewise, you can think of Q3 as the third quartile, which is the positional average below which there are 75% of the data set, or above which there would be 25% of the observations. So three partition values are splitting the data into four equal parts. That's what these quartiles do. Let us try to understand from this example. The same data starting with 24, 26, 29, 35. So how many observations are there? 4, 5, 6, 7, 8, 9, 10 and 11 observations. These are already arranged in ascending order of magnitude. So since they are 11, the middlemost observation is the sixth one, that is 72. So first we compute the median, that is 72 here. Now this 72 observation is splitting the array into two parts. This is the lower part and that is the upper part. So the lower part is 24, 26, 29, 35, 48. Now if you compute the median of this lower part, then it will be the third observation and therefore the first quartile is 29. The other half due to the median is 150, 161, 181. Again 5 observations. So the middle one is 181. So Q3 is 181. So the third quartile is 181. So 29, 72 and 181 are respectively the quartile 1, quartile 2 and quartile 3. Obviously, the second quartile and median, they coincide with each other. That was a very simple data. One can look at the big data also. We will go to an Excel sheet and see how do we compute the quartiles and what do they mean actually. So Based upon these quartiles, Q1 and Q3, see here is a diagram that shows you actually the splitting of the data into 4 equal parts, 25%, 25%, 25% and 25%. And these partitions Q1, Q2, Q3 are splitting them into 4 equal parts. It is important to notice that obviously one has to arrange the observations in increasing order of magnitude. If you don't do that, then your values of Q1, Q2, Q3 are not correct, because this is not any data that it is splitting into 25%, or neither it is chronologically ordered. You might think that you are ordering it according to time and then taking the first 25% observations. No, this is regarding the value of the response variable and you are going by the observation value and not according to the time. Okay, so when you do this, the interquartile range is defined as the Q3 minus Q1. So you are taking the difference between the third quartile and the first quartile. Now do you think that this is right, and why people are doing like this? See, when we learnt range, this is also range. This is called as interquartile range. When we learnt range, we said that we will have maximum and subtract minimum from it. Then we noticed that if there are extreme observations, then there could be an unnecessarily undue large observation, which is my real maximum, but the data doesn't say that it should be the maximum, or the other values are not okay to be called that as the maximum. So in order to remove that effect of the extreme values, you concentrate on the middle observations. You forget this 25% observations, you forget these 25% observations, which are going to affect the undue overestimated dispersion given by range. So you concentrate on the 25% of the data only and then find out the difference between the maximum value and minimum value. That gets you the value of the interquartile range. So this is another measure of dispersion used whenever the data is affected by extreme observations. Now there is always one problem whenever you are dealing with large amount of data, and that problem is of an outlier. For example, we are collecting data on the ages of human beings, ages of patients, and suddenly you find the age of a patient as 115 years. Now the question should be whether that is a real age or that is a typo or what. Now all the times you cannot go back to the raw data or raw forms that you have collected and verify. So in such cases, what to do? You have to either ignore that observation or you have to consider some different observation in place of that. You might be having some other information. For example, you have an weight of the same individual, and weight of that same individual is something, or the BP of that individual is something that gives you an idea about the age. You can do something. So we are going to look at those kind of challenges in our last session of the course, that whenever you come across such outliers or whenever you come across missing data, how to do the statistical data analysis. So right now I am not going into the details of that, but these kind of observations are known as outliers. There should be some formal definition of outlier, right? One cannot say that 115 is an outlier as far as age is thought of, but 100 cannot be called as an outlier. So one should have some kind of objectivity in determining which is outlier and which is not. So generally, if the value of the observation is outside the 1.5 into the interquartile range, so 1.5 times of that interquartile range, then you call it as an outlier. So it could be on this side or it could be on the lower side also. On both the sides it is called as an outlier. So if it is Q1 minus 1.5 into IQR, then also it is an outlier. Let us not go into these details right away because we have yet to digest the concept of dispersion. So this is again the same example where you have already computed the quartiles and then you take the interquartile range as Q3 minus Q1. Now here what will be the range of this data? The range of the data is 183 minus 24. Okay. So it will be 169, right? So this range obviously will be greater than the interquartile range. Okay. Now I would like to show you, before going in for this variance, I would like to show you what are these quartiles and for large data what do they mean. Here is a data from the clinical trials. So it's called as myeloma data from the StatExact software of Cytel. I have collected it. So these are the authors, Kral, Uthoff and Harley. They provided data of a survival study that include the survival times in months of 65 multiple myeloma patients with data on 15 concomitant variables. So here these are the variables of your patient ID, survival in month. So this is actually your endpoint. You are finding out or recording the number of months the patient survived who are affected by this multiple myeloma. So survival months is the important variable here. Then there are other variables: hemoglobin, platelet, infection, age, sex, low WBC counts, fracture, lymphocyte, myeloid. This is again one of the predictors of that disease, urea, base protein, etc. So there are several such values. Now what I have tried to do here is that, first of all, in data exploration, as we have seen, we should try to understand the data by drawing some figures, by computing the frequency, diagrams or histograms. So since survival month is an important or the variable which we are studying here, we should be knowing more about it. So with the help of Excel, I prepared the frequency distribution for this variable. Now, by now you know that what does this mean. So this 10 is from 0 to 10. This 20 is from 10 to 20. This 30 is from 20 to 30. These are the number of patients having the survivals in months below 10. So within the first 10 months of the study, 21 patients have died. But the survival of 22 patients was between 10 to 20. And we have grouped this data into a frequency distribution. If you draw the histogram looks like this. So this is not a kind of symmetric histogram. We call this as positively skew histogram. We will see this slide of positively skew when we talk about the skewness. So this is positively skew. What do we mean by that? That means the majority of the frequencies are concentrated toward the lower end, and then the frequencies go on tapering. Here you see that there is one bar which is having again a little bit more value. This is arising out of this frequency 6. So this one can call it as a bimodal data. You are having two modes here. One is here and other is at this point. Although the main mode will be here, but you are seeing fluctuations like this. So one can investigate why suddenly the deaths in the interval 50 to 60 are more, because they had started coming down up to 3 and then suddenly it was an increase and then they are lowering down. So these are the points of investigation from the statistical analysis. We think of a mixture of distributions and those kind of things. Again, those are quite advanced topics right now. So what I was trying to tell you is that if you compute these cumulative frequencies in percentages. Now what are these cumulative frequencies in percentages? See, this is 21. Then if you divide 21 by the total number of patients, and then you will get the cumulative frequency percentage for that. You go on adding the cumulative frequencies of the classes, then you will get the number of patients here. Here they are written in the percentages. Now, what does this mean? That there are 32.31 percentage of patients below 10. Here, there are 66.15% patients having survival below 20 months. What is in the numbers? It would be 21 plus 22. So there are, we will say, isn't it? We will say that there are 43 patients whose survival was below 20 months. Okay. There were 47 patients whose survival was below 30, and so on and so forth. So here, when they are represented in percentages, what does the median do? We want to find out the median. Median is the point below which there are 50%, above which there are 50%. So here 32.31 and then 66.15. So the median lies between these two. Right? The median lies between these two. The first quartile, below which there are 25% of the observations. So below 10 there are 32%. So the first quartile has to be below 10. Okay. So similarly one can think of this, and then you can calculate the quartiles here, and I have calculated them for ease now. So see, Q1 is equal to 7. Excel has a ready-made formula which computes the quartile. So 7. So as I mentioned that the first quartile has to be below 10. The median is 15. See, it is computed as quartile, second quartile, it gave me the same value. When I computed it as median, it gave me the same value because both of them are the same. The third quartile has to be such that below which there are 75% of the observations. So where would you focus? See, this is the class because it is having 76.92%. So below which? So below 40. So between 30 and 40 should be the third quartile, and here the third quartile comes out to be equal to 35. So if you want to compute the interquartile range, you will take the difference between third quartile and the first quartile. Okay, and the interquartile range will be 28 for this particular example. Okay, I suppose it is clear that how to compute this interquartile range. But the main point is, what does it indicate? What does it tell us? So 28 months is the range for the survival for the middle 50% of the patients in this study. If you think of minimum and maximum, I suppose I have computed them here also somewhere. Anyway, but the minimum, just a minute, the minimum survival is looks like that it is 1.25, and the maximum survival is 92 months. So if you take the true range, it will be 92 minus 1.5. So around 90.5, but the interquartile range is just that 28. Okay. So let us now go back to our presentation. With interquartile range also, people faced problems, that it is not based upon all the values in the data. So one has to think of some other measure which will be more robust, more sensitive also, at the time more robust also. So we think of variance. Now variance is the most important quantity in statistics because variance talks about the variation of each observation in statistics considered around the measure of central tendency. So that is, there is a linkage between the dispersion measure and the measure of central tendency here. Now how we will look at it. Basically it describes the relative distance between the data points in the set and the mean of the data set. Summarizes the square deviation of each data value from the mean. So if you ask me the formula, now in statistics there are two things. One is population and another is sample. I suppose we talked about it in our introductory session, that we always infer about the population based on a sample, because you cannot handle the population every time. So you take a sample and then you take the observations on sample. So xi we generally denote as the observation of the variable on the ith individual. X bar is the symbol used for denoting the arithmetic mean, and you compute this deviation xi minus x bar, take its square, sum it and then divide by n minus 1 here. In population variance divide by n and then you will get the sample variance and the population variance respectively. Now what is all this jugglery about? You need not bother about the formulae here. I will explain to you why this is done and what is the logic behind computing this. Just remember key thing that variance and standard deviation are related like that standard deviation is the square root of the variance. Obviously the positive square root. Again why then one needs standard deviation? Why shouldn't we satisfied with variance? We will discuss that in a while. So this is a computation of standard deviation explained here. Suppose you want to compute the standard deviation of these numbers, which actually you don't have to, because all the programs are going to give you the values of the standard deviations right away. But in order to get the insight, you should know what you are doing. So how to evaluate this formula? Again, the aim behind explaining this formula and all is to develop your insight and kindle your interest. If you get the value directly and be satisfied with that, it is your choice. But if you know what you are doing whenever you are computing the standard deviation, you will enjoy the subject more. So here the first step is to compute the mean, that is done here. Now compute from every observation you subtract that mean and take the square. Find out the number of observations minus 1. Even if you don't subtract 1, that is okay. Then you divide by that n minus 1, take the square root. Why should I explain to you here? Let me go back to the Excel thing. See, this is our data, very simple data. Number of observations are 12 and we want to find out the variance for this data. Now, if you just plot this data into a scatter diagram, it looks like this. These are the lines connecting the points. So you see that there is a spread in the data. If there would have been lesser spread, the values would have been like this. If there would have been greater spread, they would be like this, fluctuations. Okay. And what is this red line? This line is that of mean. This is the mean of the data. And I have drawn that line here. So the observations are fluctuating around mean, we say that. So each one of them is away from the mean either on the positive side or on the negative side. That is why we are calling it as mean, no? It's golden mean kind of thing. So if you take the deviations here, this is my observation, this is the mean, you subtract it and you get this value. So for example, the first observation 12 is 0.75 units away from 11.25, that is this. The second observation is 2.75 units away from the arithmetic mean. The third observation is funny, it is 2, but the mean is 11.25. Now when I take the difference, it gives me minus 9.25. So it goes here. So this distance from mean is minus 9.25 on the other side. So in this way I capture the deviations first of all. Now why do I do that? Because I want to get the idea about the entire variation in the data. So first step is to capture the deviation. This is we call in statistics as deviations. So these are the deviations of the individual values from the mean. Okay. I want to know the average deviation, that will give me the value of the some variance or dispersion. So if I take the sum of these deviations, the funny thing happens that it comes out to be equal to 0. It has to be, because this is the mean of the data. So how do you compute mean? You take the sum and then divide by total number of observations. So whenever you subtract it and then take the sum, the total sum is going to be equal to 0 because they are cancelling each other. That is why arithmetic mean is, the analogy is generally referred with arithmetic mean is as that of center of gravity. At center of gravity, all the positive negative forces cancel each other. Similarly, and that is why that particular object gets balanced. So that happens with the arithmetic mean, and therefore it is 0. So then for every data set, howsoever large data set could be, the sum of deviations are going to be 0 if you are computing them around mean. Then what to do? This is happening because of the problems of negative signs. So one way of getting rid of these negative signs is to take the absolute deviations. So there is one measure which is called as mean deviation around mean, which only takes the absolute deviations. You forget the sign and take the average. We are not going into that measure of dispersion here because this is rarely used in our domain. Another way to get rid of the negative sign problem is to take the square of the deviations. So 0.75 square is taken here, 2.75 square is taken here. So you are squaring the deviations and then take the sum of the squares, okay, and then divide by the total number of observations. Now here forget that I am dividing by 11. Suppose I am dividing it by 12. Now you divide it by the total number of observations. Then what are you doing? You are computing the average squared deviations, right? So the problem then becomes is of the units. If you have measured these in centimeters, then the variance unit becomes centimeter square. So in order to bring back to the original unit, you have to take the square root of the variance here, and that gets you the standard deviation. Okay, that gives you the value of standard deviation. So why do we compute the standard deviation? Only to get the same units as far as the spread is concerned of the considering the data, but that gives you the idea of that variation. Okay, so if that is understood, let me tell you about this difference n minus 1 and n in a very short manner. I won't go into details of that. Whenever you are taking sample and you are computing standard deviation or variance, you divide by n minus 1, and whenever suppose you are having the entire population, then you divide by the total number of objects. The reason being that this is an estimator, unbiased estimator of the population variance, nothing more than that. So it's an estimate variance. We will see about that estimate and parameter when we will talk about the statistical inference. So some software will report the standard deviation using this formula. Some will report the standard deviation by dividing by the total number of objects. Obviously they won't be much different, and they will be very very less different if your n is large. Now having computed the standard deviation, suppose you want to compare the data. In statistics always the key question is of comparison. You have to compare one data with another data. You have given the treatment to some patients and you have not given the treatment to some other group of patients. And then you want to see the difference between the means and the variances, etc. Or you might want to compare the amount of variation in some response variable x with the amount of variation in some other response variable y. For example, variation in height of patients and variation in weight of patients. The standard deviations computed for height and weights will be bearing the respective units of measurements. So, for example, the standard deviation for height could be 5 centimeter and standard deviation for weights could be 2.3 kg. How to compare these two? Whether the variation in height is more than the variation in weight or otherwise. These numbers cannot be compared because they are carrying their own units with them. So, in order to make that comparison possible, this is a measure that we study which is known as coefficient of variation. It is basically a relative measure of dispersion and it is independent of the units in which the standard deviation is expressed. How do you make it unit free? You divide the standard deviation by the mean. So, those who have learnt physics, they know how the units cancel each other, right? So, coefficient of variation, standard deviation divided by mean. So, since the numerator is also in the same measurement and the denominator also having the same measurement, they cancel each other. So, what you get is an absolute number without any units. And just to make it the comparison possible and meaningful, we multiply it by 100 and we specify the coefficient of variation in percentages. Okay. So, for this particular data, you have these observations, you compute them, you compute the mean and you compute the standard deviation. While I just thought of telling you, while computing the mean, whether it is sample or population, dividing is always by the number of observations. Don't divide by the n minus 1 whenever you are computing the mean. Then the standard deviation is computed here and you can compute the coefficient of variation and this is expressed as in percentages. So, it is 56.14 percentage of coefficient of variation. So, if you have some other data, then you could be able to compare it with that. So, let us now run through the merits and demerits of the measures, although while discussing these, I have gone through all of them. So, range, good measure of comparison as it spans the whole distribution, easy to understand. Demerits, uses only two of the observations, can be distorted by extreme values. It does not indicate any concentrations of the observations, cannot be used in calculating other functions of the observations. See, the mathematical analysis or statistical analysis that is going to follow always need that whichever measures you are defining, they should be considering all the data. They should not be only considering a few observations from the data. So, standard deviations are the first merit here is that it is based on all observations. If you throw out the outliers and compute the standard deviation, that is your choice. But with the outliers also, you can compute the standard deviation. So, handling outliers comes outside the purview of the statistical analysis actually. That is a part of the data cleaning methodology. And then when it comes that you have decided to work with the data and then compute the standard deviation, etc., then there is no question of throwing away any observations. So, the standard deviation based on all observations, it is rather complicated to define and calculate. I hope now it has not remained so after this explanation. This closely related to the most commonly used measure of central tendency. That's the main point actually. You are considering all the time sticking around the mean and then computing the standard deviation. Again, can be distorted by extreme values, capable of further mathematical treatment, rigidly defined, cannot be calculated for qualitative data. This is another problem, that since it is qualitative data cannot be expressed in numbers, or even if you explain them in numbers, they are just the codes. If you say mild is 1, medium is 2, severe is 3, that's the coding you are adapting. The data remains qualitative. So you cannot compute the standard deviations of these 1, 2, 3, or even if you compute them, you won't be able to interpret them as far as the qualitative data is concerned. So this is a drawback for that. Cannot be computed for a distribution with open-end classes. These are the formulas. You don't have to compute anywhere, I suppose. Using this formula, only should be aware of why these formula are there. They are not coming from skies anyway. So quick knowledge check. Standard deviation is always non-negative. Remember, statisticians make a difference between non-negative and positive. What is the difference between non-negative and positive? Non-negative includes 0 also. Positive doesn't include 0. So standard deviation is always non-negative. This is a true sentence. That means standard deviation can be 0, right? Now when will you think that the standard deviation is 0? Will be 0? What do you think? Do you have any idea? When can the standard deviation be 0? All the values are 0, then everything is 0. If all the values are constant, then your mean is the same, and what you are subtracting mean from every observation, so all the deviations are 0, so their square deviations are 0, so the sum is 0, so the variance is 0 and the standard deviation is 0. So whenever all the values are constant, that means there is nothing varying. So if there is nothing varying, what can be the variance? Variance has to be 0. So now if each observation is doubled, then the variance also gets doubled. What do you think? When each observation is doubled, that means you multiply it by 2, or you add the same observation to that. I will tell you the answer, you can verify yourself. The variance will be multiplied by 4. The standard deviation will be multiplied by 2. That means standard deviation gets doubled. You can check in Excel. Dispersion is the scatter in a series of values about the average. Measures of dispersion are always positive. Coefficient of dispersion is an absolute measure of dispersion. Standard deviation is half of the difference between upper and lower quartiles. This you will right away refute now, because this is nothing but the interquartile range divided by 2. Actually, that interquartile range divided by 2 is also a measure of dispersion, that is known as quartile deviation. Okay, so I mean you can learn other examples or other measures also by going through this. I would like to just show you that the proc means procedure as well as proc univariate procedure in SAS give you all these measures. You can get standard deviation, then this coefficient of variation here is given, variance is here, then mean, median, mode, range, interquartile range are all provided by the proc univariate. You can get the quantiles. Now the difference between quantile and quartile is that quartiles are only 3 measures which are dividing the entire data into 4 equal parts. For quantile, you can think of any such percentile. You can say, I want to know 47th percentile. That means I want to know the value below which there are 47% of the observations. That is called as 47th quantile. So in general, you can have, so this is 99th quantile, 95th quantile. Because you can think of anything, you might be interested in the lower 60% of the students, because above them will be the students scoring first class. So that way you can compute all the other quantiles also. So see, 50% coincides with median, 75% with Q3, 25% with Q1 and 0% with minimum, because there isn't anybody below minimum and there is everybody below maximum, so 100% coincides.